Hello. In this practical session, I want to show how do we profile our CUDA code using two profiling tools provided by NVIDIA called Nsight Systems and Nsight Compute. So we'll look at how do we interpret the results coming from those profilers. What does profiling mean? It means measuring how a program is running on the system. So for instance, how much time is being taken to run on the CPU, how much of time on the GPU, and is it using memory efficiently, and many other aspects like that. So we are going to look at the matrix multiplication examples which we took up in the lecture, both versions of them, the naive version, the simple unoptimized version, and the tiled version of it. So first of all, we are going to profile our simple matrix multiplication, the unoptimized version, using Nsight Systems. Nsight Systems is a tool which gives us a high-level overview of how our program is running on the heterogeneous system of CPU and GPU. And basically, it tells us what are the sequence of kernel calls being made and how is the memory transfer between the CPU and the GPU going on. More importantly, it helps us see if we are having good overlap of GPU and CPU compute, the asynchronous nature, which really is the ideal. So on the terminal, we profile the code using Nsight Systems by running nsys profile and then the executable name along with the parameters. We receive the output of this is a file, is a report, a profiling report with the extension .nsys rep. And if you are running it on a cloud VM with a GPU, then we copy this file back to our own machine and we open it using the Nsight Systems GUI, which lets us see a lot of things clearly. So what I did was I profiled both the versions of matrix multiplication, the simple one and the tiled one. I took the reports and I'm visualizing it here. So let's see how to interpret this, what observations we can make. Now here I'm looking at the naive version, the simple unoptimized version, and in this other tab I have the tiled version. So for the naive versions, here in red are the sequence of CUDA calls to the CUDA API being made. So basically these ones. So these sequence of CUDA malloc and CUDA memcopy, followed by the kernel invocation, and then some memcopy and CUDA free. So these are the sequence of kernel calls, and we see right now we can only see like there's one CUDA malloc and one CUDA memcopy. So why is it? Well, we need to zoom in to this part, and when we do this, we see that in fact there are other CUDA calls as well. So there is one CUDA malloc here, followed by two of them. Well, we can just zoom in further. So there's the first CUDA malloc, second CUDA malloc, third CUDA malloc. So we have three CUDA mallocs here, followed by two CUDA memcopy, and those are here. So why is it that we see the first CUDA malloc taking so much time? Well, this is because in the first API call, there's a lot of things going on which are unrelated to this particular CUDA malloc, which has to do with setting up the GPU and how the CPU interacts with the GPU. So it's a one-time configuration cost. Maybe it might be better to do a dummy CUDA call, CUDA malloc, before looking at this, so that will give us a more accurate picture. But these three CUDA malloc calls, they are really not different from each other. So all of them should take about the same time. Then we have some CUDA memcopy. And let's maybe zoom out. So here we have some CUDA memcopy, and now then there is at some point our kernel invocation. And where is that happening? So that is happening. We have to zoom in quite a bit here. So maybe I just do Shift Z and so on. So here we see this is the call to the kernel. Now, why is this such a small amount? Well, it's a microsecond. I am multiplying 4096 by 4096 matrices, two of them, and it's showing me this, and then it's showing invocation of CUDA memcopy. So I'll come back to why this is this, or maybe we can look at here itself, that what the CPU, so this is all the calls being made by the CPU to the GPU. What's happening on the GPU, we are not seeing it here, we'll see it in a moment. But at this point, the CPU is just launching a kernel, and that's it, and it is moving on. So it doesn't wait for the results of this matml kernel to arrive. And this is because CPU and GPU, they can operate asynchronously, and the CPU doesn't really have to wait for the kernel to get finished. Now, one thing to note is that after invoking the kernel, we have a CUDA memcopy here, and this is what is called a blocking call. And what this means is that this memory copy doesn't really happen until the kernel which was called before it, that has completed, and that's why it's a blocking call. So at this point, the CPU has called CUDA memcopy, but because it's a blocking call, it has to wait for this thing to complete on the GPU. Now, from the GPU's perspective, here, so the green portions are the actual data transfer corresponding to these memcopy. So here are the two memcopy calls, and here's the actual data transfer going on between the CPU and GPU. Here, CPU invoked the kernel and then moved on, and here the GPU then started executing the kernel, and it takes quite a while for it to complete. It takes quite a while. Maybe we can just do this. So we see here, and then once the kernel is completed, then the memory transfer happens from the GPU to the CPU, and that is when this memcopy, it gets completed. And finally, here we have some CUDA-free calls. So here we see the timeline of calls being made, the CUDA calls being made, and we also see a high-level view of the what's going on the GPU side. So this is what's happening. So there's some time being spent to transfer data, but the bulk of the time here on the GPU is spent running the kernel. And if I stay here, it gives me some numbers as well. So this number of, so the execution time, which we get 438 milliseconds, it actually is, it involves the overhead of profiling as well. So, and that can be quite large, but still it helps us compare the unoptimized and the optimized versions. But anyways, we do see here that it's actually the kernel which is taking the most time, and it makes sense for us to optimize the kernel. Now, how do we do that? So for that, we really need a more detailed picture of what's going on the GPU when this kernel is called. And for that, we have to make use of another profiling tool, which is called the Nsight compute. Now, we run Nsight compute in this way. So basically NCU, and then followed by executable with some options. And this will again give us a report, which is called, I'll just pull it up. So here I have opened up, so the reports are called NCU rep. And we copy it to a local machine and then visualize it on the GUI. One thing to note is that it might be that the VM, the cloud VM, might not let the profiling tool gain the very low level access it needs to collect the data. So that might be an issue with Nsight compute. There might be ways to get around this, but if you are working on a local machine with the GPU, that's not an issue at all. So I have opened this file for our naive matrix multiplication, and I want to identify what are the sources of the bottleneck. And there's quite a lot of data here, but we really only need to look at a few numbers. So we do see that the compute throughput here is 10%, and the DRAM throughput, so there are different types of memory. DRAM is the slowest one, and I'm more concerned about how well the DRAM memory bandwidth is being utilized. And that is 20%. And these numbers are quite low. And here we see the Nsight compute complain that we are observing low compute throughput and low memory bandwidth utilization and so on. And it's telling us to look at these things here for more details. So maybe we just look at warp state statistics. And here here it's telling us that each warp, so right now maybe think of it as a collection of thread, and each thread is spending these many cycles being stalled waiting for some memory operation to be completed. And this gives us an idea about what's happening. So basically in this, if you look at the naive matrix multiplication code, each thread is running this kernel, and in each iteration of the loop, it's making requests to global memory reads. And because they have high latency, so a thread makes a request and then it gets stalled for the data to come in. And that's the problem we are having here. So Nsight compute. So this is the issue. So the number which we see here, the conclusion which we make is it has low compute throughput, but that is because the threads are, every time they are getting stalled, waiting for data to arrive. And this tells us that really we need to improve the memory access pattern. And this thing can also be looked here. So this is the machine code for the kernel. So for this particular kernel, the GPU machine code, we don't need to worry about this. But here we get an indication of, on average, how much does a thread get stalled when executing these instructions. And we see here a lot of yellow bars. Whenever the thread is trying to load something from the global memory, LDG, we have stores, we have stalls. Now, well, the question might be that here we saw that in each loop iteration there are two loads from the global memory, whereas here we are seeing a lot more, and that has to do with the fact that the compiler did some loop unrolling. So in each iteration of the loop, it's maybe doing 4 of these or 8 of these together, and that's why but the key point is that because of these requests to global memory, the warps are getting stalled. And what's also happening is that because the global memory is seeing such a huge volume of memory requests, and they are they are not in a very good pattern because each thread is individually sending its own memory request, then it slows down. So the DRAM is not able to serve these read requests as well. And we are not able to, because of this, make use of the memory bandwidth to the full extent. So here's the point, that we have been seeing that for a GPU, the compute capacity, peak compute throughput is much more as compared to how much data can come in, the peak memory bandwidth. But here, we are not able to even use that memory bandwidth which is there because of like each thread making so many requests to the global memory that everything gets clogged up. And then so for our tiled version, we can see how things have improved. So maybe let's first look at the Nsight system report. And here basically it's the same sequence of the CUDA API calls. But when we look at a high level at what's going on the GPU, then we see that here the span of this kernel execution as compared to the naive one is smaller. And if we hover over this, it says that it takes around 88 milliseconds. which is something like 5 times faster than the Nine version. And if we look at the Nsight compute report for this, then we can see how things have improved. So the trial version here, the details. So we do see that as compared to 11%, the compute throughput has increased to 40%. And the reason why that happened was now we are using the memory bandwidth in a better way. It's 85%, way more than the 20%, which we saw for the naive version. And the tool tells us that the workload it's actually using the memory well here, so it's high throughput. And here, as compared to each, on an average, each thread waiting for getting stalled for 225 cycles, here it's only 10 cycles on an average. That's also much better. And oh, sorry, it's not 9 cycles, it's actually 60 cycles. Each warp spent 60 cycles being stalled for the memory operation to get completed on an average. And we can look at the same kind of analysis at the machine code for the kernels and tile matrix multiplication. And we see that it's only at this one particular point where threads get stalled, waiting for data to come in from the global memory. And that is in the code, that is here, when each thread is loading up data in the shared memory from the global memory. So for A and B, so loading to the A and B tiles. Note that we don't have loop unrolling going on here, and I think it's because of the thread synchronization. Because of the compiler couldn't unroll this. So that's all. So we see like what kind of information is given to us by these profiling tools and how to interpret them. See you in the next lecture.